Next, we skip over this part and move on to this critical step where we call our DFL module for distributed focal loss. This module takes only one argument, the box tensor. Now, there's a lot happening here, and it's best understood if we break it down into its components. First, the DFL module contains a convolution, and the weights associated with the values from 0 to 15 were defined during initialization and remain unchanged throughout. We know that our input box tensor has the shape 1 by 64 by 6300. The code unpacks these values and reshapes the tensor. Then it transposes dimensions 4 and 16, resulting in 1 by 16 by 4 by 6300. At this stage, we can visualize the raw logits. Next, we apply softmax to dimension 1, meaning each of the 16 values will be normalized. These softmax values are then fed into the convolution layer, which produces a single value for each of the 16 sets. Let me try to explain this better. Let's focus on our 15 by 20 feature map level and approach the problem from a different angle. We start with two tensors, but for this operation, we're only concerned with the box tensor. This tensor is then passed into the DFL module. In the DFL module, we now have 64 box values for each grid cell. These 64 values are reshaped into 4 sets of 16. For each set, the 16 values are softmaxed and normalized to represent the left, top, right, and bottom values of the bounding box for each grid cell prediction. If, for example, we focus on the left values and expand to better visualize it, when the convolution is applied, each of the 16 values for every grid cell is multiplied by the corresponding weights from 0 to 15. These weighted values are then summed up to obtain a single consolidated value for the left, top, right, and bottom boundaries of each grid cell. Unlike other convolutions, where the weights are updated during backpropagation, the weights for DFL remain fixed. This means the model is encouraged to generate a set of 16 values for each grid cell that, when multiplied by these fixed weights, give the best approximation for the ground truth bounding box labels. To visualize this, I generated a feature map-like visualization of these values after the softmax has been applied. I think it's interesting because you can see how each of the 16 values represents a step in a scanning process. For example, the left features represent the left boundary of the bounding box. They scan from left to right, indicating the strength of how many grid cells we need to move left from each grid cell prediction center to determine the left boundary. Similarly, for the top features, we see a top-down scan corresponding to the roof of the car, identifying the top boundary. The same applies to the right features, which identify how many grid cells are between the center and the rear of the object. Finally, the bottom features scan from bottom to top to define the bottom boundary of the bounding box. This scanning behavior is key to how DFL refines the bounding box prediction and ensures the model generates accurate location estimates for each grid cell. Now, these feature maps that we just saw correspond to all the grid cell predictions for our 15 by 20 feature level. However, what if we focus on just one of these grid cells? I have chosen this particular grid, index 6150, for reasons that will soon become clear. As we've already seen, each grid cell contains 64 values, 16 each for the left, top, right, and bottom. We can print these raw, unnormalized values and visualize them for each side. While this gives us an idea of their relative importance, what we actually want is to normalize them using softmax so that they sum to 1. This normalization makes it clear how much each value contributes to the final result. That's what we do here next, and now we can plot these normalized values. I've also created a helper function that calculates the expected value, which is the final output of the convolution. To verify our calculations, we directly print the DFL output for this grid cell, and as expected, it matches the values in our plots. For better comparison, here are the plots again. First, the unnormalized values, and second, the softmax normalized values. All right, with that, we're ready to continue in VS Code. Now the output of the DFL step, along with the anchors, will be passed into the decode bounding boxes function. Let's go there. Inside decode B boxes, we call another function, distance to bounding box. At this point, we now have our bounding box dimensions, and we also know the anchor point center for our grid cell prediction. Using both of these, we can compute the top left corner, x1, y1, and bottom right corner, x2, y2, of our bounding box. These coordinate values are absolute, referenced from 0, 0. Since the x, y width height flag is set to true, we step into this function to convert these values into the bounding box center, xy, along with its width and height. We then concatenate these updated values and return the final result. Now we can quickly run this in Colab as well. I've created another helper function, plot distance to bounding box, to visualize all this information in one place and solidify our understanding. Here we can see that for grid 6150, we have the DFL output, which provides the distances needed to construct the bounding box. Using the anchor point at x equals 10.5 and y equals 7.5 for this particular grid, we can compute the absolute coordinates accordingly. This also reveals an interesting property of the predictions. The grid cell's prediction, represented by the black dot at the anchor point, is not necessarily at the center of the final bounding box. This happens because the model does not predict the bounding box directly. Instead, it predicts the distances from the anchor point to the left, top, right, and bottom edges. As a result, depending on these distances, the final bounding box may be shifted relative to the grid cell center. However, this aspect allows for more precise localization, as the box is not constrained to be perfectly centered on the anchor point. Now that we have all of these, let's go back to our feature map overview and visualize the distance values for the left, top, right, and bottom, which define the bounding box. Next, we need to scale these dimensions. Since our feature map is 15 by 20, but our input image is 480 by 640, we scale back by multiplying with the stride of 32, the same factor that originally downsampled the image to this feature level. After doing this, our new coordinates remain in absolute terms, but now they match the 480 by 640 scale of the original image. And as expected, this bounding box perfectly aligns with the car in our input image. This works because the stride scaling ensures that we correctly map predictions from the feature map back to the original resolution. The model has effectively learned to predict distances in the lower resolution space, and by upscaling, we recover the precise positioning in the full resolution image. However, one potential limitation is that if the feature map resolution is too low, fine details in small objects may be lost, leading to less precise localization.